The solenoid is a foundational architecture in electromagnetism, a tightly wound helical coil of wire designed to channel an electric current. Its behavior is governed by two specific parameters: the current flowing through the wire, I, and the turn density, N, which represents the number of loops per unit length. This top right diagram provides a cross-sectional view of the system. To analyze the magnetic properties, we slice the coil along its axis. Red dots on top indicate current flowing toward us, while crosses on the bottom indicate current flowing away. Reducing the 3D coil into this 2D geometric model allows us to isolate the magnetic vectors and begin the calculation of its internal field. Using the right-hand grip rule, curl your fingers along the current. Your thumb points right, establishing the field vectors. In an ideal infinite solenoid, the internal field is perfectly uniform and parallel to the axis, while the external field is exactly zero. Our next step is to derive the exact mathematical magnitude of this internal field, before testing how it behaves when the solenoid is no longer infinite. Using an idealized environment allows us to establish the baseline rules of the system before we calculate the influence of physical, real-world boundaries. To solve for the magnitude, we apply Ampere's law. This relates the integrated magnetic field around a closed loop to the total electric current passing through that loop. On the left of this diagram, we place a yellow rectangular Amperian loop, labeled ABCD, across the solenoid wall. Segment AB sits entirely inside the uniform internal magnetic field, while segment CD sits outside the coil, where we assume field strength is zero. Positioning this geometric boundary across the solenoid wall creates a mathematical trap, isolating the internal field from the external void. We split the loop integral into 4 segments. Paths BC and DA are perpendicular to the field, so their products are zero. Segment CD sits in the zero field external region, vanishing as well. This leaves only segment AB, simplifying to the field strength multiplied by its length. Due to symmetry, 3/4 of the calculation disappears, leaving only the field magnitude multiplied by the interior segment's length. For the total enclosed current, N turns per unit length over length L gives N times L turns. Multiplied by current I, this forms our right side. Equating the path integral BL to this enclosed current times magnetic permeability, we simply cancel the L's to reveal the final equation, B equals mu naught times N times I. This result shows the internal magnetic field is independent of position. It is determined exclusively by turn density and current. While this derivation holds for infinite coils, real solenoids have physical ends where the uniform field begins to bow outward. To calculate the field at any specific point within a finite coil, we use this generalized trigonometric formula. Point P represents the observation location. Angles alpha and beta measure the sight lines from that point to the physical left and right ends of the coil. This trigonometric relation links the physical dimensions of the coil directly to the magnetic field strength, allowing us to account for the effects of finite edges. We can test this formula against our ideal model by placing point P deep inside a solenoid that stretches to infinity. In this case, both angles alpha and beta expand to 90 degrees. Since the sine of 90 is 1, the sum equals 2. This cancels the denominator, returning the field strength derived using Ampere's law, B equals mu naught and I. To find the boundary condition at the very edge of the solenoid, we move point P to the physical opening. Angle alpha remains at 90 degrees, but angle beta collapses to 0. The sine of 90 degrees is 1, and the sine of 0 is 0. The sum is exactly 1, leaving us with half the field strength of the interior. The geometric limits of the system dictate that the magnetic field strength precisely at the opening of a solenoid is exactly 1/2 of the maximum value found deep within its interior.